Swayam Prabha. Digital India. Educated India.
Hello students, welcome back, and we are now discussing the application of the concepts of thermodynamic potentials from the second law of thermodynamics in real systems. So what we have seen so far is that a set of equations known as Maxwell's equations are extremely important in thermodynamics. And here we find that the fundamental equations of thermodynamics can be made more usable from the Maxwell's equations, so that irrespective of what the system is, whether it is an ideal gas, real gas, a liquid or a solid, I would be able to find out quantities like du, dh, ds under constant temperature volume condition, or ds, that is the infinitesimal change in entropy under the conditions of constant temperature and pressure, in terms of measurable properties such as Cv, Cp, alpha and kappa. And you see that all the expressions, they are now expressed in terms of easily controllable properties like temperature, volume and pressure and other measurable properties of the system. Now in this lecture, I'm going to do some exercise to derive the relationships shown here for the measurable thermodynamic response functions when you have some information about the system you're working on. And for this purpose, I have chosen the simplest of the systems, which is 1 mole of a monatomic ideal gas. Here we know that the ideal gas equation is given by pressure into volume is equal to universal gas constant R and temperature T. Also, from the kinetic theory of gases, you might have come across this particular relationship where this is the internal energy of the gas, and you know that this for 1 mole of the substance is given by 3/2 RT. Now in this case, this number is 3/2 simply because I have a monatomic ideal gas. So my question is, for this system, how shall I find the specific heat at constant volume? Obviously, by definition, since Cv is del U del Tv, and I already know what U is, therefore I can write this as del T of 3/2 RT under constant volume. If that is so, I know that this is a universal constant. It doesn't have any dependence on the temperature or the constant volume that you are working with. Therefore, I can say that Cv is equal to 3/2 R into del T operating on T under constant volume condition, right? Now, so what is the result? Therefore, I can very easily say that Cv is equal to 3/2 R. So, for 1 mole of this substance, I can find out that the specific heat at constant volume is going to be a constant, and the value of this constant is 3/2 into R, that is the value of the universal gas constant. Now, if I had n moles of this monatomic gas, what would be the value of U? I know that U is an extensive property. So, for n moles of the ideal gas, I will have U is equal to 3 by 2 n RT. If that is so, then what is going to be CV? CV once again is del U del T V. So, this must be given by 3 by 2 R into del T of NT under constant volume condition. Now, since I am dealing with a constant amount, either 1 mole or n mole, therefore, I am working in a system which is closed, and therefore CV actually is nothing but CVN, or you have a constant number of particles for this system, and therefore I would say that in this case I must be having, for the capital N particle system, or equivalently small n moles of the substance, CV is equal to 3 by 2 R into N into del T of T at constant volume. Therefore, I would say here the specific heat at constant volume for n moles of the substance, that is equal to 3 by 2 nR. So, as you can see very easily that it is possible to generalize our discussion on 1 mole of a monatomic ideal gas to n moles of the gas as well. Now, if I move forward and think of how I can find out, for example, the isobaric expansion coefficient alpha, that by definition is given by 1 by V del T P. Now, in order to evaluate alpha for 1 mole of a monatomic ideal gas, where do I start from? Look at the expression of alpha. In order to find out alpha, I need to take a derivative of volume with respect to temperature at constant pressure. So, I need a relationship between volume, temperature and pressure. So, which expression gives me that? Obviously, the equation of state for the monatomic ideal gas is giving me that relationship, and therefore, since I am taking a derivative of volume with respect to temperature, I am going to use the equation of state to write down volume as RT by P. So, what is del V del Tp? So, del V del Tp now turns out to be R by P into del T of T under constant pressure condition. Just because, simply because I am maintaining this constant pressure condition, I could place P outside the derivative, and therefore I say that this is nothing but R by P. Look, the definition of alpha involves not only this partial derivative but also a 1 by V in front. Therefore, what is 1 by V into del V del Tp? That turns out to be R divided by PV. Now I already know that PV is equal to RT. So I can further simplify this expression. So this quantity is alpha and this is equal to R divided by RT. So what is the final expression of alpha? I cancel R from the numerator as well as from the denominator, and what I have is alpha is equal to 1 by T. Now what does this expression tell me? It tells me that if I know the temperature at which the ideal gas is present, then I can immediately say that the isobaric expansion coefficient is equal to 1 by T. Now let us go ahead and look at another quantity that we have come across already, and this is the isothermal compressibility of this ideal gas. So by definition, what is it that I have to do? I have to evaluate this partial derivative del V del P T and then multiply it with this quantity 1 by V, add a negative sign, and the result would be my isothermal compressibility kappa. So once again, since I require some relationship between volume, pressure and temperature, where do I start from? I would start from the ideal gas equation of state. So once again, I start by writing down V is equal to RT by P. I have to take a derivative with respect to P at constant temperature, and therefore I can write that del V del P T is equal to del P of RT by P under constant temperature condition. If that is so, I can always take out R into T from this derivative, and the result is I need to find out del P of 1 by P at constant temperature. This is nothing but taking a full derivative of 1 by P with respect to P, and the answer is minus RT by P square. Clear? Now once again, I am going to simplify this result. And also I note that I have minus 1 by V in front. Therefore, let me check what is 1 by V del PT is. This is nothing but dividing the right hand side by V. I am going to simplify this a little more. I am going to write down this as P into V, and in the denominator then I have P square into V. So V would cancel out and I will have minus 1 by P on the right hand side. Therefore, what is kappa? Kappa, that is equal to minus 1 by V into del V del PT. This by this expression is nothing but 1 by P. So now you have been able to show that kappa is equal to 1 by P for an ideal gas. So if I move forward and then use these three relationships that I have already derived and use them in this expression that Cp minus Cv is equal to alpha square Tv by kappa, what is it that I can find out? I can directly find out what Cp is going to be for an ideal gas. Now, so let me write down what is alpha square Tv by kappa is. So, what is alpha? Alpha is 1 by T square multiplied by T into V divided by kappa. Now, kappa is equal to 1 by P, and therefore, I will write down this as 1 divided by 1 by P. So, this term turns out to be, I make it T, and so PV divided by T. Now, what is PV? Since it's an ideal gas, I know this is equal to RT. Therefore, this term is nothing but RT by T, and this is equal to R. Therefore, for 1 mole of an ideal gas, we have been able to show that Cp minus Cv is equal to R. Is that clear? So, all I had to do was I used this relationship that we have derived from the application of Maxwell's relation to the definition of Cp and Cv and put in the values of alpha and kappa of the ideal gas, and what I find is Cp minus Cv is equal to R. Now that we have got Cp minus Cv equal to R for 1 mole of this monatomic ideal gas, I know what Cv is, that is 3 by 2R. So, what is Cp? Cp in this case is going to be R plus Cv, that is equal to R into 1 plus 3 by 2. And therefore, Cp for 1 mole of this monatomic ideal gas turns out to be 5 by 2 R. So, that tells me that knowing the ideal gas equation and also the internal energy as a function of temperature in this case, we can also evaluate what the specific heat at constant pressure would be. And here is a summary of all the results that I have shown to you in this connection, in the connection of 1 mole of a monatomic ideal gas. We can actually evaluate any quantity that may be important to us during the practical application of the system at hand. So, if I have 1 mole of a monatomic ideal gas, as you can see, if I ask the question, what is going to be the change in internal energy under isothermal condition for 1 mole of a monatomic ideal gas? Then I am essentially asking for the value of del U del V T, which is nothing but the internal pressure of the ideal gas. Now, if I put in the values of alpha, T and kappa here for the ideal gas, I should be able to show that this value is nothing but equal to 0. Now, look at del H del PT. This is the question that I am asking here, is what happens to enthalpy of 1 mole of a monatomic ideal gas if I increase its pressure at constant temperature? Now, this is the expression of del H del PT, and we have already shown that alpha for this gas, that is equal to 1 by T. Therefore, what would be the result? So, alpha T would be equal to 1, which means the term within the bracket will vanish, and therefore, once again, for 1 mole of a monatomic ideal gas, this quantity is going to be equal to 0. If you have a given system under a constant temperature condition and you would like to change its pressure and see if the entropy of the system increases or decreases, how will you do that? You will just have to have the information regarding the alpha value of the system. So here again, del S del Pt will be equal to minus of V by T. Similarly, I can find out what del S del Vt is, and I have already derived this expression for you. So let us have a look at what is mu Jt for an ideal gas. As you see, once again, since alpha for 1 mole of an ideal gas is equal to 1 by T, the term within the bracket is going to vanish. As a result, mu Jt for an ideal gas is equal to 0. And this is a relationship that I have already derived for you, and I have shown that this is equal to R. I will leave it as an exercise for you to show that Cp minus Cv for n moles of an ideal gas is actually n into R. All you will have to do is use the proper relationships here for n moles of the ideal gas and find out what happens to Cp minus Cv. And finally, I would like to mention that you can take this exercise of finding out alpha and kappa by knowing the equation of state of a real gas. So, for example, if I have 1 mole of a van der Waals gas, its equation of state is given by this expression. So, it gives you a functional relationship between pressure, volume and temperature of the gas. Now, here I have two characteristic constants, A and B. These are the two constants that can be determined in the laboratory by subjecting the real gas to changes in pressure, volume and temperature. So, these are characteristic macroscopic constants. And these macroscopic constants, you can very easily show, are actually related to the non-negligible size of each particle constituting the real gas, as well as the amount of interaction that the particles have with each other. But still, I would like to emphasize over here that A and B are macroscopic quantities which are determined in the laboratory, although they reflect the extent of underlying interaction and the finite size of the molecules involved. Now, if you know the pressure and volume of the real gas and the temperature at which they are present, you can now play around with the volume expression for volume and find out what alpha is. Similarly, you can also find out what kappa is, and I'm going to leave this as an exercise for you to find out what alpha and kappa are. So, I will also give you an exercise to find out what is going to be the variations of del u del Vt, del h del Pt, del s del Pt, del s del Vt. And as you see over here, what you have is all you need to know is alpha and kappa, which you can very easily find out from the equation of state for 1 mole of the ideal gas. Similarly, this is a very important exercise that you see here, and this is the Joule-Thomson coefficient, and you can indeed show that mu jt will depend on the value of the characteristic constants A and B. And one can show what exactly the expression for mu jt would be. And finally, since you know alpha and kappa, you should also be able to find out what Cp minus Cv is for a 1 mole of a van der Waals gas. So in my next lecture, I will show you the final expressions for all these quantities so that you can take the check your own work against these results and really convince yourself that if you know one thermodynamic relationship like the equation of state, then you know you have a complete information about the thermodynamic properties of this system. Here, again, I would like to conclude by saying that the Maxwell's relations not only gives you some idea about how to generalize the fundamental equations of thermodynamics for practical applications, they also tell you that you need only 3 variables to define the equilibrium state of a system. That is simply because if you have 3 quantities, you can always express the 4th quantity in terms of these 3 variables. So that is another enormous simplification that the Maxwell's relations give you, and that is, in spite of having an Avogadro number of particles, in spite of having a macroscopic dimension of the system, in spite of having defined a quantity energy which is not intuitive, or defining a quantity like entropy which follows from the second law of thermodynamics. Thermodynamics is a very simple description of the system in terms of 3 variables and 3 variables only. Thank you.